Hello, everyone. My name is Lefteris Koutsoulakas, and I'm doing a PhD at the University of Leeds. Today, I will talk about my PhD research with the title Smart Net Zero Energy Structural Control. Structures around the world suffer from dynamic vibrations, which are mainly caused due to earthquakes, wind loading, or even human action. So my PhD research aims to minimize, if not eliminate, these dynamic vibrations in order to ensure structural integrity and human comfort. To do that, I use as a case study a real skyscraper called the Rottweil Tower. The Rottweil Tower is a 246 meters tall tower located in Germany. It is owned by a company called ThyssenKrupp, and it is a test tower for high-speed elevators. It also offers 360-degree views of Rottweils to the visitors. And the company installed a hybrid mass damper on the tower in order to dissipate the dynamic vibrations caused by the wind loading. The term hybrid means that the system can act either as a passive conventional tune mass damper or as an active tune mass damper using the installed actuators and the control algorithms. More specifically, the system consists of a 240-ton mass, a dashboard damper, spring element, and electric actuators that are acting in two orthogonal directions. Moreover, the system possesses damping and stiffness adapting capabilities. However, we will not consider this within this presentation. The actuator capacity of the system is 35 kilonewtons, which after a literature review that we prepared, we realized that it is considered to be relatively small when compared to other actuators that are installed on similar size structures. So this is one of the key challenges that we have to deal with. When the company contacted the University of Leeds, they told us that in order for their high-speed elevators to operate properly, the top floor displacement cannot exceed the 200 millimeters. So as a first research target, we decided to keep the top floor displacement to be between the 200 millimeters limit. Moreover, the actuator manufacturers told us that in their control scheme, the hybrid mass damper could not achieve better performance than the passive conventional tune mass damper, which is something that you don't expect to hear, since the hybrid mass damper is developed to be the better version of the passive system. So as a second target, we decided we wanted to enhance the performance of the hybrid mass damper and thus limit this small actuator capacity effect. To do that, first, we developed a robust control scheme where we designed different control algorithms that, and we wanted to investigate the parametric uncertainties that could occur due to modeling errors, environmental effects, damages on the structure, and see how they affect the performance of the hybrid mass damper. Moreover, we developed a reinforcement learning control scheme where we wanted to investigate the performance of a state-of-the-art control algorithm that was proven to be very efficient in different control fields, for example, in robotics. Today, I will only focus on the reinforcement learning control scheme because of the time constraints. Generally, the reinforcement learning algorithms try to mimic the way that a human brain learns. For example, here we have our algorithm, the agent, that interacts with an environment, our structure, that has no previous knowledge about, and by trial and error, tries to learn how to properly control the structure. We provide a reward function to the agent for every correct action it takes, and we also penalize every wrong action it takes and in this way we manipulate its behavior. We used an algorithm called Deep Deterministic Policy Gradient, or DDPG, which consists of two deep neural networks, one being the actor and one being the critic. The actor is responsible for taking all the control actions in order to control our environment, and the critic is responsible for evaluating every control action that the actor takes based on the reward function that we provided. We chose this algorithm because it has a continuous action space, meaning that every control action can take any value between the given limits. In our case, the limit is 35 kilonewtons. And it was proven to be very efficient in robotics, autonomous driving, building energy consumption forecasting, and more. For its training, the algorithm designed 1,850 different scenarios or episodes, and for each episode, the algorithm was receiving a cumulative reward. After a certain number of episodes, our algorithm was comfortable on controlling our structure. Moving to the simulation results, first we will compare the performance of the DDPG to a very well-established controller within the field, the linear quadratic regulator, or LQR, to the structure without any type of control, and to the structure with just a passive conventional mass damper. The evaluation criteria will be, of course, the top floor displacement to be ideally below the 200 millimeters, the top floor accelerations, which are directly related to human comfort, and the power consumption of the system when operating actively. Starting with the displacement, as you can see here, both the LQR and the DDPG managed to decrease the top floor displacement to be below the limit, the desired 200 millimeters limit, in contrast to the passive mass damper and the uncontrolled case. More specifically, the DDPG had the best overall performance, and it managed to decrease the top floor displacement by 22.4%. When considering the acceleration, here the DDPG it was clearly the best controller, since it managed to decrease the top floor accelerations by 35.8%. In order to achieve that performance, the DDPG achieved a saturation factor of 4.6% in the actuator force, in contrast to the 7.3% of the LQR. This basically means that the DDPG reached the 35 kilonewton limit almost 3% less than the LQR, making it a more efficient controller. We can also observe this here when we investigate the power consumption over time for the two controllers. As you can see, the DDPG required less maximum power consumption to operate in contrast to when compared to the LQR. You can also notice here that the total cumulative energy that the DDPG required was slightly higher than the LQR. However, this is not necessarily a bad thing, because a large portion of this energy is a dissipative energy, and this brings us to our next target, which is to develop a harvesting system in order to harvest all this dissipative energy, store it in a battery, and then provide it back to the system when it's needed, and work towards making it a self-powered system. Moreover, we want to use the semi-active capabilities of the system that I briefly mentioned earlier in order to considerably decrease the power consumption of the system while keeping a very good vibration dissipation performance. And we also want to use all the data that is gathered from the monitoring system that is equipped on the tower in order to develop data-driven controllers and compare their performance to the purely mathematical ones and evaluate their performance. Thank you very much for your attention. I want to thank my supervisors, Dr. Nikolaos Nekitas and Dr. Petros Aristidou, and ISTRAC for inviting me today. Thanks.
Thank you, Lefteris. So we have some questions straight away from Steve. So question number one, were there any investigations into what was causing the movements of the tower?
Yeah, it's due to the wind loading. That is because, as you can see here in the picture, there is no other tall structure in the area. So the wind loading was causing these dynamic vibrations on the structure.
And if we know the if we know that it's wind, then is there any way that categorization or understanding the physics of that source of the vibration could help improve the system further?
If I understand well, is it if we understand better the wind loading, will this help us make a better control system?
Yes. Yeah, exactly.
Yes, actually, that's a very interesting point. In my simulations, I modeled this wind loading based on the sensors that they have on the structure. The company provided me the data, so we try to model the wind loading as accurate as it could based on the measurements that we have. So of course, yes, we need a very accurate wind loading to model our system. However, we also test our algorithms to see their robustness. So we want to alter the wind loading and see how our algorithms will perform.
Okay, thank you. That was an interesting answer. Yeah. So my question was, I saw some of the results, and you showed improvement of 20–30%. Yes. Based on the baseline, and you showed that the passive TMD alone was getting you perhaps 10 or 20% improvement. Yes. And I was surprised that didn't sound like very much.
Yeah.
So then other circumstances you might expect a TMD to give you quite a lot more benefit, or even just the passive one. I wonder if you could tell us a bit more about that. Was it to do with the tuning of the TMD, or was it to do with the mode shape to the vibration, or was it something else?
Yeah. First of all, everything starts with the sizing of the TMAS damper. However, the passive system, especially, that's one of the key problems of the passive system. The passive system cannot adapt. That is not active. It cannot adapt to change. So, assuming that the TMAS damper, the passive TMAS damper, was tuned perfectly in the fundamental mode of the vibration of the structure when it was built, after all these years, the dynamic properties of the structures change due to environmental reasons, due to damages, aging, and this makes the passive system less effective because of the changes in dynamic behaviors of the system, and it cannot adapt to these. That's why it has a deteriorated performance.
Thank you. No, that was interesting, because I was curious about that.
Yeah.
Thank you very much, Lefteris.
Thank you very much.
Good presentation.